Okay, g'day everyone. In this video I'm going to be covering a two-way ANOVA that includes interaction. So this is without a doubt the most difficult form of a two-way ANOVA with interaction that you get taught within this course. If you though want to perform just a single two-way ANOVA on its own, it virtually follows the exact same procedure as what we have here. So what I recommend doing is just having a look through the lecture notes and having a look through the prac notes and also the lectorial notes to see how a two-way ANOVA without interaction is performed. If you can't follow the video that I've got here, or it's just not making sense for whatever reason, then by all means please shoot me a message either over Facebook or send it to me via email and we'll sort it out. Okay, so I'm going to continue working with the data set that I was working with in the previous prac on one-way ANOVAs. What we're going to be looking at in this case, in the one-way ANOVA, we looked at situations in which we wanted to identify the relationship between a numerical variable, in this case being diff, and a given categorical predictor variable, and I believe we looked at color. What we want to do in this two-way ANOVA is we want to be able to extend the situation so that we have more than one variable being included in the analysis. So in this situation, we'd like to look at the relationship between difference and packet and color. Now just remember, for those of you that are just tuning into this video that haven't seen the previous one, this refers to the candle data. So if you go to the prac materials, you'll see that within the Minitab files, one of them is the candle data, so get a copy of that. And now in terms of this diff, this refers to the difference between the initial length and the end length. So the way that we calculate that, in terms of naming this, you just double click on that cell and you can type in whatever you want. I'll call it diff. You may want to call it diff to follow everything that I've done in this. And then to generate the data for that, just go to calculator. We're storing the results in diff, and then it's the difference between the initial length and the end length. And whilst I'm at it, I may as well just give you a bit of an overview of what this data set is. This project team wanted to see how different components of a candle affect the amount in terms of the length of the candle that's burnt in a fixed time interval. So the variables that they were looking at is to see if they could identify what influence the amount that was burnt within this fixed time. Let's say it was a minute. Is the packet it came from. Packet could refer to brand as well. The color of the candle, the initial weight of the candle, the angle that it was burnt at. So 90 degrees obviously refers to perpendicular to the surface. That obviously burns at a different rate than if you were to have it at, say, 60 degrees. So they wanted to analyze that effect. And then we've got the start length, the end length, but really what I want to look at in this video is there a relationship with the overall difference. So we've calculated that. Now when you're performing a two-way ANOVA, we need to have what's referred to as balanced data. And in order to have balanced data, well, the first thing you need to do is obviously identify your response variable, and you need to identify the categorical variables that you want to use. But before I go into that, I just want to give sorry, these things sort of come to me as I'm talking, and I know that it's a little bit out of order at times, so I apologize for that. But the reason why we like to use a two-way ANOVA in contrast to a one-way ANOVA when we can is because when you're dealing with a one-way ANOVA, remember the one-way ANOVA is just between a single response variable and a single categorical variable. When you're doing this analysis, it doesn't care about any of the other variables whatsoever. So the results that you get are just the results between difference and packet. Doesn't take this variable into consideration, doesn't take that into consideration, angle, etc., etc. So those variables could actually be playing a very important part in how the difference is calculated, but it hasn't even been taken into consideration whatsoever. So when you do the one-way ANOVA, it just considers the variables that you give to us. A two-way ANOVA is nice, a much more better way of being able to represent the data because you can include another variable. So here we're going from just having one categorical variable to two categorical variables. So in terms of identifying the variables that we've got, we need to have a numerical response variable, in this case being the diff. So the response variable that we're looking at is diff. And then in terms of the predictor or the factors, now remember I mentioned this in the previous video, categorical variables are quite often referred to as factors, especially in ANOVAs. So the two factors that we've got is color and packet. So these are the two variables that are going to go into it. And what we now need to do is we need to formulate our null and our alternative hypothesis. Now, another really cool thing about a two-way ANOVA is it actually performs multiple tests in one situation. So what we see within here, we've got our three null and alternative hypothesis, is if we just look at the first one and have a read through it, it says there's no difference in expected diff between the different colors. Now remember, expected is another way of writing mean. So there is no difference in the mean differences, in the mean diff between the different colors average over the packets. Now what you see when you do a one-way ANOVA, and I've got the example of the one-way ANOVA here when we were looking at color, is that the mean difference is the same for each color. So you see that this is exactly the same as we've got in this first component. There is no difference in the mean diff time, or expected diff time, not time, between the different colors. The only bit that we've included here is we've averaged over the packets. So in the one-way ANOVA, where it didn't take into consideration any other variables, in the two-way ANOVA, it is considering another variable. So it's identifying the relationship between diff and color, but taking into consideration how packet influences the results. So that's the first one that we're looking at, but obviously we have more than one factor or more than one categorical variable. So we have the exact same thing here. The only thing that's changed is color and packets have swapped. So this null and alternative hypothesis is dealing with how color has an influence on diff. This null and alternative hypothesis refers to how packet is having an influence on diff. And the last one refers to the interaction between the two. So when we sort of bring these variables together and they begin to interact, does their interaction have an influence on the diff? Now, in fact, what I've actually written up here is almost you can create a template. And so what I've actually done is I've created a template below that will be released with this file. So you can see here RV, I should probably write this up here. So in this case, RV equals response variable, F1 equals factor 1 variable, F2 equals factor 2 variable. So you'll see that when you compare these two, that essentially all you need to do is just insert what you've got for your individual case, and that will be perfectly fine. You're not going to get marked down for using this. That's exactly what we want you to do. Not to say that you can't write it yourself, but if you're unsure, definitely use this template. Okay, so we've got the three different null and alternative hypotheses that we're testing. So just to summarize again, testing the relationship between color and diff, testing the relationship between packet and diff, and then testing the relationship between the interaction of color and packet and diff. So that's what we want to do in this case, and let's generate that output. And we want to have the output produced here. So I'll just have Minitab output. Okay, so if we go into Minitab here, we need to have, so we go to, look, I feel terrible, my memory is absolutely horrible, but I'm not sure if I went over that we need to have balanced data. So just very quickly, when you're doing a two-way ANOVA with interaction, you firstly need to identify if the data is balanced. So the way that we can identify that is if you go to stats, tables, cross tabulation and chi-squared. It doesn't matter what you put in for the rows and columns in terms of the order. Click OK, and what we have is this output. So what we hear is this is just a cross tabulation between the different packets and the different colors. So what we have here refers to the fact that there were 6 blue that came from packet 2. This refers to that there was 6 whites that came from packet 3, and so on. You'll notice that for each of the different subcategories, or the combined, they all have equal values. So there's all 6 for each of these different situations. This is what you need to have when they say balanced data. This is what they mean. When you do a cross tabulation between your factors or categorical variables, however you like to put it, you need to have equal values. Even if all of these were 6s and the last one was 5, unfortunately it won't work. You can still perform a two-way ANOVA without balanced data. However, if you want to perform one with interaction, you need to have this balancing. So sorry if I've already covered that. I've done so many tutorial videos this morning that I forget what I've said in each of them. Okay, so let's generate them. Anyway, so coming back to this, let's generate the Minitab output. Now, if you're working at the Uni Labs, you'll be used to seeing Minitab version 16. If you're working at home, you may have downloaded the student copy. That's Minitab version 17. I'm working with the student copy that you can download from the site, which is version 17. The instructions on how to do a two-way ANOVA are slightly different. Well, they're not hugely different, but they're not so difficult that you can't understand what's going on. So what I'm going to do here is, obviously I'm going to demonstrate it in terms of Minitab version 17, but for anyone who's unsure as to how to do it in Minitab version 16, please send me an email, send me a message on Facebook, or post on the Facebook page, and I'll send through the instructions on how to do a two-way ANOVA. But here what we want to do is we want to go to Stat ANOVA, and we want to perform a general linear model, fit general linear model. So I'm going to get rid of all of this. The response variable that we're looking at here is diff. The factors that we're looking at, so remember there's multiple factors, is we're looking at color and packet, but we also want to include the interaction. Now how we include the interaction is we click on the model button, and you'll see that they've got all the factors and the covariance. So we're actually not too worried about covariance, this is just factors. So if I want to include the interaction term, you just hold shift to highlight both, and interactions through order number 2. And you'll see, sorry, it's already there. So I'm going to get rid of that. So if that wasn't there, you'd highlight those two, click add, and you'll see here in terms of what they have listed in the terms of the model, we have color, packet, and then color star packet, and that star represents the interaction. So this is the interaction between color and packet. Click OK. OK. Oh, and sorry, we go to graphs, and I can't remember what it is by default, but all we want to have is these two graphs. Click OK. OK. And we've got the results here. So the first thing, now this output again too is going to look slightly different. I'm not concerned about any of this stuff. This is stuff that will be covered in another video, especially when we start doing general linear model. But all I want to do, so we're going to send the selected lines to Microsoft Word. The main thing that we're interested in, or the key thing that we're interested in, is interpreting these p-values. So we've got the 3 different p-values that we've got here. And so that's what we're going to have a look at. And the way that we interpret the p-values is exactly the same as what we do for every other case. So it's the exact same method as what we have for what we had for the previous video in terms of the one-way ANOVA, and then for all the chi-square testing we've done, and tests of proportions and all of that. So for the first one, this p-value with respect to color, we see here, it's very simple. So p-value, I always like to write it out this way, p-value color is equal to 0.00. How do we interpret this? If we remember correctly, let me just quickly pull up a file that I believe I had. Yes, so this is that summary sheet that I was referring to in the Prac 1 video. If you want to know where this is, go to the Facebook page. Sorry, go to the Blackboard page, and if you go to look at Robert's summary notes, it's for topic 4. And you'll see there's this table within it. We've got less than 1%, so we have very strong evidence against the null hypothesis. So here, so we have very strong evidence against the null hypothesis. So because we've got obviously very strong evidence against the null hypothesis, we're going to be accepting the alternative hypothesis, and then you can almost copy exactly what you've got here. So therefore, Control V, there is a difference. There is a difference in expected diff between the different colors averaged over the packets. So that's essentially saying that there is a relationship, a certain type of relationship. I went about this a lot in Prac 1, in the Prac 1, the Prac for the, when I said Prac 1 before, I meant to say the Prac on the One-Way ANOVA. So if you watch the One-Way ANOVA videos, you'll see me talking about the different p-values and how to interpret them. But essentially the main thing that I was going through in those videos too, when I was talking about the different types of relationship, based upon how the two-way ANOVA defines a relationship, we seem to have a relationship here. So that relationship is that the mean differences, or the expected differences, remember they're interchangeable terms, is between the different colors is the same. So there is a difference. So when we take the total diffs and we separate them out based upon colors, we find that the averages are actually different, and that's including the packet being taken into consideration. Okay, so in this case here for the packet, let's have a look at the p-value that we've got. We see here that we have a p-value of 0.00. So in terms of the interpretation, it's going to be exactly the same. The only thing that's going to change around is it's going to go from packet to color and color to packet. So this will become packet. We have very strong evidence against the null hypothesis. Therefore, there is a difference between the different packets averaged over the colors. So that's what I mean. Like, this stuff tends to look like it's a lot of work. What you find is there is a lot of copy and paste, Okay, so in terms of the interaction, we've got 0.049. So this here too is going to be, in terms of how we write this up, it's going to be slightly different because the p-value is different. So as the p-value, interaction, is equal to 0.049, so it's just under 5%. Well, I'm not sure how to interpret that. Let's go to the table. Between 3% and 7%, we have some evidence against the null hypothesis. So we have some evidence against the null hypothesis. We may as well keep it consistent. It's a null hypothesis. So as a result, in this case here, it comes to your judgment call as to whether or not you think that that is strong enough of a p-value to say there is an interaction, or whether or not it may actually be lending to the situation in which there is no interaction. In this case, I think given that it's under 5%, that's a quite a small p-value, and as such, I'm going to, yes, say that there is an interaction. So again, how do we write that up? Well, we can just go to the alternative hypothesis that we had. I mean, that's what we're concluding with, and we can just copy and paste that into here. Now, I don't want you to think that you can always just copy and paste like that. Sometimes you do have to word it a lot better, but because these null and alternative hypotheses have been worded so that anyone can sort of interpret that result, you don't have to have an understanding of statistics to essentially read that, or you don't need to have a great understanding of statistics to read that. So you can just use that again. But if it was a lot more formal, like you're using maths notation, if you will, throughout, then you probably would have to convert it over. So we're just going to have here, so it'll be therefore the difference between the expected diff for the different colors is different for the different packets. So that's just essentially saying that there is a relationship between the interaction of colors and packets for the diff values. Okay, so the next thing that needs to be discussed is if there is, as I've got here, if there is evidence of interaction, generate an interaction plot. So what we want to do is we have found that there is some evidence of interaction, but maybe we want to get a visual analysis to back that up. And one way of doing that is to do what we call an interaction plot. So we go into Minitab. These graphs will be used later. And let's just go to Stat, ANOVA, Interaction Plot. And in this case here, the response is the diff variable, and the factors is color and packet. We click OK. And so what we need to do is we will send this graph to Microsoft Word. Hopefully it's put it in the correct spot. Yes, it has. So it's put the graph up here. So now we need to discuss the interaction plot. Now, defining interaction in terms of the visual analysis is incredibly difficult. However, as an introductory sort of interpretation, and this is what I would recommend in terms of how you would approach all the interaction stuff that you're going to be dealing with this subject, is that when we look at these sort of situations, the way that we can define no interaction is essentially when we have parallel plots. So what I mean by that is, if we have the shape within here, we would expect the others to have a similar shape. So see how this, if we're comparing it to the brown line, this purple line to start off with seems to follow the same sort of behavior. Down, down, well, it's sort of changed a little bit, and then it moves up. So it's sort of followed the general trend of what we've got here. So these are sort of parallel. In that case, we would say there's no interaction between the two. Although, in comparison though, if we look at the green, we see that the green cuts across, and it's definitely showing a completely different behavior, and definitely not a sort of parallel behavior. So when we have these sort of situations in which their lines are crossing over, and then they're almost following the same trend, that's when we can identify that interaction has occurred. So it appears that there's interaction between this area and this area for these two. So what is that between? So that's green and pink. Oh no, white and pink, I apologize, between these two for the different packets. And the same is true when we compare blue with, what's the purple one? Yeah, so blue and yellow here. We see that there is some interaction here, and then also the shape of the graph is significantly different. So you just need something really short and sweet to cover that. So we observe that interaction appears to occur between the different colors. So between the different colors for the different packets. And then you might want to include in particular that of the, so in this situation it is the pink and white for the different packets. So remember, I apologize because these colors here don't match up with the colors that they've got here, but there seems to be a strong interaction between these two and a strong interaction between the second two. the different packets. Oops, sorry about this. And that of the, so these two colors are, so purple is yellow and blue is blue, and that of purple and blue for the different packets. Okay, so the next thing that we need to talk about is the assumptions of, sorry, I apologize. Before we jump into the assumptions, we need to talk about the R-squared adjusted. Now, if you're unsure about how to interpret the R-squared adjusted, I explained this a lot more in the previous prac for the one-way ANOVAs, but essentially it's a measure of how close the model is that you're generating to the actual data that you've got. So, obviously 0% means it's captured nothing. 100% means that it's captured everything, so there is no difference between them whatsoever. So what we want to have a look at is, well, let's jump in and have a look at the R-squared value that we've got within here. We can get rid of that graph here. So the R-squared was obviously in the other one, I wasn't thinking. But in this case here, we've got an R-squared adjusted of 50.68%. So let's just jump into that. So let's just write that out. The R-squared adjusted of 50.68% indicates that 50.68% of the variation in diff relative to, in the variation of diff across the color, packet, and interaction is explained by the model. So I guarantee you could almost take that as a template as well. And you could include that in the end. And in fact, actually, I will do that right now. So may as well, oops, Control V. So the R squared adjusted of, so you need to put R squared, so the underscore R squared adjusted indicates that R squared adjusted of the variation across difference, and so this would be, obviously this becomes factor 1, factor 2. Now you can even actually go one step further with this and goes when with I'll probably write scaled according to the number of parameters in the model. So this is explained in detail in the one-way ANOVA in terms of how the R squareds are actually adjusted. The R squared adjusted is different to the R squared, and it's because it makes it relative to the number of terms in the model. So that way we can have a complete understanding of it. So I'm just going to add this to the end of the definition that we had before. Okay, so now let's jump into the assumptions of the model. So the assumptions of the model are exactly the same as what we have for the one-way ANOVA. So we need to have normality of the residuals. We need to have a random nature. Well, 2 and 3 are all looking at testing essentially the equality of variances, but we want to have a random nature between the residuals versus the fitted values, and then we need to have equality of the variances. So in terms of the two graphs that we had before, these both can be used to explain that. So for the first one that we're looking at, the normality of the residuals, that refers to this graph here. So we're going to right click, send graph to Microsoft Word. So we go within here, and what we want to see is essentially this red line. I believe it could be I believe that in Minitab 16 this is a blue line and these dots are red. They've just reversed it for Minitab 17 for whatever reason. But essentially we want to have all of these dots to be as close as possible to the line. Now what we see unfortunately in this case is that it does seem to be a sizable gap in many spots. So it only really seems to be doing well right in the center. So you just write something very simple along the lines of, so we observe that the residuals tend to move away from the normal line in many areas. As such, the assumption of normality of residuals, which is what we're doing here, may not be satisfied. So you can't say for certain that it isn't a normal distribution, but essentially here this is a fairly weak one. So you could almost conclude that they aren't normally distributed. or should I say, it's a very, very loose definition. So we might want to actually include that. So let's just say that I'm just trying to think of the best way to type this. So we observe that the residuals tend to move away from the normal line in many areas. However, overall, we conclude that the data is loosely normally distributed. And then instead of having as such here, we'll have, however, the assumption of normality of residuals may not be satisfied. Okay, so let's go into the random nature. This will definitely need to go into another page of the residuals versus the fitted value. So that's what we have, within this graph within here. So if we right click here, we go to send graph to Microsoft Word. Hopefully that put it in the right spot. Okay, so what we essentially want to see is we want to see a random nature within here. We don't want to see any what they call fanning effects. So fanning effects is when it sort of goes up and then down, or alternatively goes down and then up, or one of the two. And what we see within here is that, this does seem to be relatively randomly scattered, but there does seem to be clumps. So like if we take this grouping together, they seem to be relatively the same. And that's what we want, because when we have that sort of similarity, that means that we have, generally that's an indicator that we have equal variances. But there does seem to be a sizable difference between this data, and then say if we put these two together, and then these two. So this one here, you could almost bunch up with these ones, and you would say that they're relatively equal. Then you have these two which are fairly equal, and these two which are fairly equal. So unfortunately what we see in this case is we have clumpings of their being equal. So I would approximate that when we do the test for equal variances and we get the graphs, that there's going to be three separate structures. There's going to be, and what I mean by structures, three separate clumpings. Clumping for this data, clumping for that data, and clumping for that data. So again, we just need to write a simple summary of that. So there appears to be multiple, I guess I'm just trying to think of the best way to word this. There appears to be multiple groupings in which the residuals have constant variance. And so when I say constant variance, I just mean they're looking exactly the same, therefore the variance we would expect to be the same. However, overall, the variances appear to be extremely different between the groupings. Therefore, the variances do not appear to be equal. As such, the assumption of equal variances may not be satisfied. So this is just, we sort of have very strong evidence to say that they are different, but we can't say it conclusively without a formal test. And coming back to it, I also mentioned this in the Way Anova prac. There is no test that we teach you in this course to identify whether or not it is definitely normally distributed or not. This is just a visual interpretation. But when we're looking at the quality of variances, this first one is a visual interpretation, but then we have a formal method to test it. So that first one, as I said, what we've got in terms of the first one, there seems to be multiple groupings in which the residuals have constant variance, i.e. here, here, and here, but with that one moved over into there. However, the overall variances do not appear to be extremely different between the groupings. So they do seem, you would expect that the variance between this group and this group would be much different. This would be much larger than that group because these are more bunched together. But I could be wrong. I'm pretty sure that it will be that way. Okay, so in terms of the equality of the variances, what we want to identify is that for each of the subcategories, are the variances equal? So we can write it in a long-winded definition, or we could just say all variances are equal for each, in this case, color, packet, combination. It can be just as simple as that. And then the alternative hypothesis is that if the null hypothesis is that they're all equal, the alternative hypothesis is that at least one is different. So how can we perform this test? So I can kill this now. No, do this now. Excuse me. We go to stat, ANOVA, and you've got test for equal variances. So the response variable here is diff, and here we've got 2. So we've got color and then packet. Click OK. So we want to have this graph within here. So I'm going to send this graph to Microsoft Word. Okay, and I've gone into the wrong one, sorry. And here we have it here. So I meant to have this before that, so let me just quickly move that. Okay, so as I predicted, and I'm very happy with this, we see that we have these clumpings between these smaller amounts, and then we have a couple of larger groupings. So that seems to fit well with these smaller amounts that we have within here, and then two different ranges where we have larger clumpings here. So I'm not sure, so this one and this one probably match up with these two, the smaller ones, and then the longer intervals that we've got here, where I imagine would correspond to these two. However, the main thing that we're looking at though is the actual variances themselves. Now, I don't know if this is just my computer or if this is Minitab 17, but I know that in Minitab 16 you'll see dots along all of these lines. Now, what we want to see, those dots refer to the standard deviations of the actual different individual combinations. So the dot that you would see within here is the standard deviation for blue, the blue color for packet 1, and then this is blue for packet 2, and so on and so on. Now what we want to see is all of these dots to be lining up. We're not really concerned about this. It's mainly just these dots. These refer to confidence intervals. So here we've got a p-value of 0.249. So here, so the p-value of, and so this is equal variances. I always like to write it out this way. You don't have to do that. So you know exactly what test you're referring to. Equals 0.249. Okay, so how do we interpret that? Let's jump to the table again. So we've got above 10%, and we have insufficient evidence against the null hypothesis. So let's write that out. So we have insufficient evidence against the null hypothesis. Okay, so in this case, we're not going to be rejecting the null and accepting the alternative. Here we have very strong evidence to say that we can't reject the null. And as such, the variances for each of the color packet combination, the variances are equal for each of the color packet combination. So therefore, as a result, the variances are equal. And then from here, we just need to have a short summary over this, the assumption. So you can write this in as such: the assumption of equal variances is satisfied. So this is a case, and this will happen quite a bit, where what you think is happening within this sort of a graph doesn't actually become translated when you do the formal test. That's fine. You can't look at a graph on its own every time and get the exact interpretation. That's why we don't use graphs on their own. That's why we have these formal tests, because graphs can be incredibly misleading. The result of that p-value is not misleading at all. There is no misinterpretation of it whatsoever. Okay, so now we just need to have a summary of the assumptions and the overall interpretation. So we've done the test. We've identified for each of the p-values, those that are having an effect. We found that in this case here, that for color, packet, and the interaction, they all had an effect on the overall difference. And that of the assumptions, whilst the normal probability plot wasn't satisfied greatly, we did find that the most important, and sorry, I did mention that before, but the equality of variances assumption is the most important, has been satisfied. So whilst the assumption of normal probability of, whilst the assumption of the residuals, just found a better way of writing it, residuals being normally distributed was only, it's not minutely, but I guess it was only satisfied, I'm just trying to think, like to a medium extent. I'm just going to write to a medium extent, and I'm sure it'll come to me after I start typing the rest. So medium extent, the assumption of equal variances was found to be true. So as I said, as that's the big assumption, that's been satisfied, and the other one hasn't been violated, tragically, we can be confident in our solutions there. So therefore, we can be confident in the results of the test. Has only been satisfied I'm just going to leave it as medium. I couldn't be bothered wasting anyone's time me sitting here to try and think of it. Okay, so that's all there is to do in terms of a two-way ANOVA. So I'm going to leave you guys there. As I said, if you've got any questions whatsoever, please send me a message on Facebook or post on the Facebook page and tag me into it, or you can send me an email. So, yep, I hope that was informative, and let me know how you go with that. Okay, bye.